Okay, it seems to have slowed down a bit, so I'll get started. So, good morning everyone and welcome to Professor Peter Budd's talk on materials chemistry. This is part of the Meet the Academics event that's hosted by Uni of Manchester ChemSoc and Chemistry Pass. Professor Budd will be giving a short presentation followed by a question and answer session. If you do have any questions, please just write them in the chat and one of us will read them out for you at the end. Feel free to add questions at any time, but please don't spam the chat so loads come through so that everyone can focus on the reader. This session will also be recorded and the talk will be posted online at a later date. We'll do our best to ensure that only the speakers visible in the video that's published, and we'll discard for everything else. Please make sure that your audio is muted, and we would also recommend turning your video off and not including your full name if you're uncomfortable, and particularly if you're under 18. And finally, a number of people have asked about receiving a certificate of participation for this talk. If you want to, you can submit a short piece of work summarising the talk and bringing up the key ideas. Please just refer to the reminder email that you received for more information about this and a sign-up link. This will only be open to school students up to A-level or equivalent, and that includes everyone who hasn't entered uni yet. So I'll just pass over to Professor Budd now and we'll get started.
Well, thank you very much. I'm just going to see if I can share my screen and hopefully now, can everybody see that?
Yes, yeah.
Yeah, excellent. Now, sometimes you may find there's a little string of other people's faces down the side of the screen, but you can minimize that so you can see everything on the screen. Okay, so I'm Professor Peter Budd, and it's really good to speak to you all and to tell you a little bit about what goes on in Manchester in terms of materials chemistry. So I go back a long time in Manchester because I was a student in Manchester myself, right back in 1975. I started as an undergraduate in Manchester and I got my BSc. I went on to do a PhD. I then went off to work in industry for 8 years. I worked for the oil company BP at a time when they were very interested in doing lots of things other than oil. My PhD and a lot of what I did when I was working for BP has to do with polymers. I'm a professor of polymer chemistry. Now, we're going to be talking about materials chemistry in general. And materials, well, that's all the stuff around us that we make use of in one way or another. And so an awful lot of chemistry is really about materials. And as chemists, we're interested, first of all, in understanding what materials are made of. In fact, we even go right to the very beginning and create entirely new materials. But then we have to understand how their chemical structures relate to their properties and the ways in which we're going to use them. And I'm going to talk about a little bit about some of the things that I'm interested in my research. I'm interested in making new polymers, in two-dimensional materials, and in particular in applying them for membranes for molecular separation. So I'm going to say a little bit about each of those three things. But first, perhaps I should introduce a few of the other people involved in materials chemistry in Manchester. So as well as myself, we have quite a few people whose research is mainly to do with materials chemistry. You can see some of those people here. It covers a wide range of different types of materials. We have a lot of interest in graphene and other 2D materials. We have interest in materials that are important in relation to their radiation resistance or important for their nuclear properties. We have a large group interested in making molecular magnets that might be useful for future generations of computers and all sorts of other things. So a wide range of materials research. And I can only touch on a tiny bit of what we do today. And of course, materials isn't just about chemistry. We interact with people in other departments in Manchester, in the School of Materials, in chemical engineering, in physics, elsewhere. And indeed, in our research, we interact with collaborators across the world. But in terms of my own research, the sorts of things that interest me are things that are going to be useful to people. And so a lot of my research is about trying to make materials that we can use to ensure that we have clean air, safe water to drink, green energy, better health, and sustainable ways of making the things that we need in life. So I'm going to focus on three things very briefly today. First of all, about polymers, and in particular about a group of polymers that are important because of their ability to soak up little molecules. I'm also going to say a little bit about graphene as an example of a two-dimensional material. And I'm going to talk about membranes that involve both the polymers and graphene. And these are membranes that might be used on an industrial scale for their ability to select one molecule over another. But let's start with polymers. Now, many of you may have come across polymers in school, in your chemistry studies, and you probably know that polymers are substances composed of giant molecules, what we call macromolecules, giant molecules made up of a large number of smaller units. And many of the things that we use, and many of the things that you will see when you look around you are actually polymers. And indeed, many of the things that make up our bodies are polymers, things like the proteins that make up our hair and so on. But I'm going to talk about a particular type of polymer, which is important to us because we invented these polymers, myself and a colleague, right here in Manchester. It's a class of polymers that we refer to as polymers of intrinsic microporosity, or PIMs. And the words come from, well, we call it microporosity because in these polymers, when they pack together in the solid state, there's little bits of space, what we call free volume left, little tiny spaces, less than a couple of nanometers in size, that little molecules can get into, and that's important for the way we use them. And we call it intrinsic microporosity because it arises from the design of the polymer structure. In other words, as chemists, we can think about how to create a molecule, a big molecule, which, because of its structure, has certain properties that are useful. The very first PIM that we made here in Manchester, there are quite a few now, but the very first one we call PIM1. And you can see an example of the structure on the screen. I also have a bit of a model with me here, if you can see that. And the thing about this polymer is, first of all, if we look at the backbone, it's all rings. It's made. It's like a little ladder. If you're a little molecular-sized person, you could climb up the ladder. And what that means is that in the backbone, we don't have any single bonds like most polymers about which rotation can occur. That restricts the ability of the chain to swivel around and reorganize itself. But as well as that ladder structure, we have something else in the structure. We have spirocenters. Now, spirocenters here is where we have a carbon atom, which is a part of two 5-membered rings. And what that does is it puts a bend in the chain. And so we end up with a chain which is both rigid in the sense that it can't rearrange very easily, but also has many, many bends in the chain. And that's the basic concept of these polymers that we call polymers of intrinsic microporosity. So if we think about a normal polymer, it actually has a relatively flexible backbone. And so we can think of a bunch of those polymers as like a bit of snakes, if you like. They can wiggle around, they can reorganize, and so they can pack space reasonably efficiently. Now, we can also design polymers which have very rigid, straight structures. But again, they tend to line up and interact very strongly with each other. But what we're doing is to try to create polymers which are rigid in the sense that they can't change their shape very easily, but nevertheless have a wiggly structure. It's like the difference between spaghetti and crispy noodles. And these rigid, contorted polymer chains can't fill space efficiently. There's bits of space left over. And that's where little molecules can get in and sit happily. And that's important for the way we use these polymers. Now, the thing about that polymer PIM1 is that it's actually soluble. It can be dissolved in certain solvents, and because it can be dissolved up, it can be processed. And actually, that's what makes these polymers different from many other microporous materials, materials that could otherwise be used for the same sorts of applications. This is much easier to turn into a form that makes it useful. We can isolate it as a powder, and I've got some PIM1 here. You can see it's a bright yellow polymer. It's also very fluorescent, which means that if somebody's in the laboratory and they're working with this polymer and they're a bit clumsy, we can follow the fluorescent trail very clearly wherever they've been. But also we can process it to make a coating or turn it into a film or indeed make fibers. And so we can turn this polymer into many different forms that are useful for the way in which we wish to apply it. And one of the features of this, the feature which arises, the way we try to design this polymer, if you like, is that it readily takes up, through a process we often call adsorption, little molecules. And a sort of experiment which is often done for studying these sorts of materials is to study how nitrogen gas is taken up at low temperature, in fact the temperature of liquid nitrogen, minus 196 degrees centigrade or 77 Kelvin. And what we find is that at that temperature, that nitrogen is very, very readily taken up at very low pressure, much lower pressure than atmospheric pressure by this polymer. In fact, it behaves as though it has an effective surface area of perhaps 800 square meters per gram of material. Now, there is a commercial application for this polymer, and I have it here. This is a mask. Now, in the current situation, you may have seen very many masks made by the company 3M, which is one of the major manufacturers of personal protective equipment. This particular mask has cartridges which are designed to absorb organic vapors. So they're used by people in the workplace where they would otherwise be exposed to organic vapors. And so it's there to protect people at work. And the cartridges actually contain something called an activated carbon. That's a very useful and relatively cheap adsorbent. But the difference with these particular cartridges is that there's a little window on the side. And as that cartridge is used up, because it doesn't last forever, you need to change those cartridges at intervals. As that cartridge is used up, a little red bar moves across that window. And that tells you how much of that cartridge has been used and gives you an idea of when you need to change the cartridge. And our polymer is the key thing that makes that little sensor work. So that's a way in which that polymer is being used right now and is available commercially. But of course, in our research, we're looking at lots of other potential ways to use that and similar polymers and other materials. Well, that's a little bit about the polymers that we refer to as polymers of intrinsic microporosity. And I'm going to come back to them when I talk a bit more about membrane applications. Let's think about another type of material for a bit. I'm going to think about two-dimensional materials. These are materials which are just one atom or perhaps a few atoms thick, but nevertheless can have very large lateral dimensions. And I'm going to talk about the most important, if you like, the best research member of that family, the one for which Manchester is famous, and that is graphene. Now, if you've ever drawn with a pencil, you've probably made graphene because a traditional pencil has as its lead graphite. And graphite is made up of layers of carbon with the carbon atoms arranged in sheets in a hexagonal pattern. And essentially one of those layers is graphene. Graphene is a two-dimensional sheet of carbon atoms in a hexagonal arrangement. And just getting one of those layers gives you something with very interesting properties, something that is potentially very useful. Actually, nowadays, graphene is used, the name is used for a whole family of materials, because sometimes even if you have just a few layers, not necessarily just one layer, it can still be useful for certain applications. So some of the things that are called graphene actually have a few layers, but they're still very, very thin. They're still essentially two-dimensional. Now, the guys who isolated graphene were Andrei Geim and Konstantin Novoselov here in Manchester. They isolated graphene and reported it in 2004, which actually is exactly the same year when we, myself and a colleague, published the very first paper on polymers of intrinsic microporosity, or PIMs. So both graphene and PIMs have been around and been researched on for about the same period of time. So Andre and Kostya, they won the Nobel Prize in Physics for what they did in 2010. I'm afraid I haven't got a Nobel Prize yet, and I don't suspect I shall. But I still think we've got some interesting materials that we've done a lot of interesting work on. Now, what Andre and Kostya did was really quite simple and yet also very clever. In order to get one single layer of atoms from graphite, they simply used sticky tape to repeatedly thin it out until just one layer was left. A very simple process, but actually it needed a lot of clever equipment to actually show that that is what you had got. Now, that's a very good way of getting a little bit of graphene for physics experiments. It's not a good way to get something that you would want to use commercially. You can make small amounts of graphene that way, but you wouldn't want to make very large amounts. So there are other ways to try to get graphene or something like that. One way is something called chemical vapor deposition, where you take a gas, it's usually methane, a carbon source, and it's deposited on a substrate which helps the reaction, often copper, and it's reacted at high temperature. And if you get it right, you can get a very thin single atom thick layer of carbon, which, if you're clever, you can then transfer from the substrate onto something else where you want to use it. Another thing which is often done is to take graphite and exfoliate it. That is to break it apart to create a dispersion in the solvent. And you need energy to do that, and that can be done, for example, using ultrasound. And that's the way in which we create dispersions, which can then be used to make mixtures of graphene with other things. And we'll see some examples of how that is used. Now, I've talked a little bit about the polymers that we refer to as polymers of intrinsic microporosity, or PIMs, and I've talked a little bit about graphene. But actually, the two are in a sense quite similar. The rings in a PIM are quite like the rings in graphene. They actually interact with each other quite effectively. And indeed, PIMs can stabilize graphene dispersions, and we can make films which are a mixture of PIMs with a little bit of graphene. And we'll see later how those might be useful. Now, why is graphene so interesting? Well, it has many intriguing properties. It is, of course, very, very thin. But it's also surprisingly strong for how thin it is. It's stretchable, it's stiff, it has an extraordinarily high electrical conductivity, which is the basis of some potential applications, also a high thermal conductivity, which is another reason why people want to use it in various applications. But the things that particularly interest me in my research is its high surface area, and also the fact that in its most perfect state, it's impermeable to pretty much anything, even the tiniest atoms like helium. A hydrogen ion can squeeze through, but very little else can get through unless there is a defect. But it has a lot of surface that things like to stick to, and we can use those properties. Actually, the theoretical surface area of graphene is 2,630 square meters per gram of graphene. That means if you have a gram of graphene and you think about the two sides of a sheet, that's the equivalent of 10 tennis courts of area. I should say that the PIMs I mentioned earlier, they have about 3 tennis courts of effective area in a gram of the polymer. There's quite a lot of effective surface just in the polymer. But graphene is also a perfect barrier if it's in a perfect sheet. And so it makes, if you like, the world's thinnest balloon. And again, those two properties together enable us to use it to manipulate the way in which other molecules are taken up or can migrate through a film which contains graphene. graphite can actually be oxidized to something that can be exfoliated in water as something that's referred to as graphene oxide. And graphene oxide is interesting in itself. It loves water, and actually it can be made into a membrane. This isn't a single sheet, it's actually layers of graphene oxide flakes, but that type of membrane is surprisingly, extraordinarily permeable to water, but when it's dry, it doesn't let anything else through. And that as well is something that's really interesting and something that we're making use of. So I've talked a bit about polymers, and in particular the polymers we invented in Manchester, the polymers of intrinsic microporosity. I've talked a bit about graphene as an example of a two-dimensional material. There are others also we're working on in Manchester, but I've just focused on graphene today. And now I want to talk a little bit about a way of using both of those materials, and that's in membrane separations. A membrane is a layer of material between two phases which acts as a selective barrier to specific molecules or particles. So we can take a mixture, and the stuff that comes through the membrane will have a different composition to what we call the feed, the mixture we took in the first place. And we're interested in membranes that can separate mixtures of gases. So we're interested in things such as how to take carbon dioxide out of blue gases to help tackle climate change, or to take oxygen from air. You may not realize it, but if you've ever flown on a commercial aeroplane, you've probably benefited from the fact that there is actually a membrane system on board many Boeing and Airbus aircraft. And it's actually used to separate air. It is not used currently for the air to create the oxygen that you breathe, although potentially it could be. It's actually used to take oxygen out of the air to create a nitrogen-rich inert gas, which is then fed into the fuel tanks as the fuel goes down, so that you don't get a potentially explosive mixture in the gap above the fuel. So it's a safety feature that helps to keep you safe when you're in the air. So that's just one example where air separation membranes are important. But as well as gas mixtures, we're interested in separating liquid mixtures. So for example, taking bioalcohols, which are potential fuels which have been obtained from biological matter, and purifying them for use, or taking water and removing impurities or salt from it to give clean water for drinking or other purposes, and a whole range of other potential applications. Let's think a little bit about what makes a good membrane material. Well, first of all, the whole idea of a membrane is that it has to be selective. If we want to take one thing out of a mixture, we want that one thing either to pass through the membrane or to not pass through the membrane. So there has to be selectivity for one species over another. But a membrane must also show high permeability. That means a lot of stuff has to be able to go through the membrane, because otherwise we would need so much membrane that the process wouldn't be economic. We could never actually run it. So we want both of these things, selectivity and permeability. Now, the problem that we face as researchers is that we can design materials that are very selective, but often materials that show high selectivity have low permeability. We can design other materials to be very permeable, but materials that show high permeability. There's a trade-off between selectivity and permeability. And we can show this on a graph, a double logarithmic plot of selectivity against permeability. In fact, in 1991, a guy named Lloyd Robeson took all of the gas separation data for polymers that had ever been published and plotted them all on a graph like this. And he drew a line, it's that line there, the 1991 upper bound, and in 1991, there were no polymers which performed better than that line. Most polymers actually have quite low permeability. There are only a few that are very permeable over on the right-hand side of that plot, and they tend to be low selectivity. Now, in 2005, in collaboration with some researchers in Germany, we published the first gas separation data on the polymers that we refer to as PIMs. There's PIM1, and also we looked at another PIM at the time that we called PIM7. And we demonstrated that these polymers, as well as being much more permeable than the vast majority of other polymers, also broke that upper bound. Well, time moves on, because in 2008, Lloyd Robertson said, well, the upper bound has moved now. So he took our data and data a few other polymers and drew a new line. So now we researchers, we had to try to do even better and find new materials that did even better in terms of how they perform. And in fact, ourselves and colleagues in other places in England and elsewhere across the world have created new polymers, mostly PIMs, which have pushed that upper bound even further. And so we can see how research has improved what is possible. And because these plots are on a logarithmic scale, that's a big change that we're seeing over that time. But these polymers aren't yet in commercial use, because for commercial use, you need a lot of other things to be right before you'll persuade a big company to spend a lot of money trying something out on their plant. And one thing is that you need to maintain performance over time. And what we're doing is we're designing polymers to trap a lot of space and to have a lot of internal surface. But nature tries to squeeze out any odd space and any odd surface that one has. And so there's a process of physical aging. It's a reversible process. It's not the polymer degrading or anything, but over long periods of time, little motions occur which try to squeeze out that space that we work so hard to get into the material. And so a lot of our research now is finding ways to control that so that the membranes keep their performance over time. And one way of doing that actually is to make use of graphene. We can take a PIM, we can add a very small amount of a graphene-based additive. It's actually taken graphene oxide and we've chemically modified it. And we've shown that that can actually help control aging. So it's one of the strategies we're using to improve the long-term performance. So here we have an example. We've taken two different things, both arising out of research in Manchester, and put them together to create something that works for a particular application. Well, in Manchester, we're exploring many other ways of using PIMs and graphene for membrane separations and for many other different applications. Just to mention a few, we're looking at the purification of biobutanol using a membrane process called pervaporation. And here again, a combination of PIM and graphene can be particularly good. We're also very interested in finding better ways to capture carbon dioxide. And PIMs love carbon dioxide, so we're looking at ways of making use of that to help tackle problems related to climate change. And another big environmental problem is dealing with impurities in water and in creating clean water. And a whole range of different types of membranes, including graphene oxide membranes, are being explored for that sort of application. So here we have a few little examples of the sorts of things that we're involved with in Manchester in terms of just one aspect of materials chemistry. We can't cover everything in one short talk. If you want to know a little bit more about graphene membranes and their practical applications, there is a video you can find on YouTube. And it's not part of the series, but there are also a whole load of other videos about chemistry at Manchester that you can find on the Chemistry at Manchester YouTube site, Canberra. And of course, you can follow on Twitter and other social media what's going on in Manchester. But for now, I shall hand over to our chair for any questions that you may have.
Fab, thank you. That was a really good presentation. We've got loads of questions, to be fair. First of all, kind of a career-related one. We've got someone who's a second-year undergraduate and they've applied for materials and physical chemistry for their third-year project. So what kind of group projects can they be expecting, and will they be working with nanopolymers?
So depending on who you go for your supervisor, there's a whole range of there'll be a whole range of projects in terms of the topics that are available. If you were to come to do a project with me, then it would almost certainly involve developing membranes. and it would involve certainly the sorts of polymers I've been talking about, because that's a lot of what we're interested in at the moment. Of course, we have one little problem at the moment, which is COVID, which means that you probably won't be able to do much laboratory-based work, at least at the beginning of the project, if we're talking about September. And we're hoping that by the time we get to past Christmas, you will be able to do some laboratory-based work. But that does mean that we outside the laboratory, which will involve not just reading literature, but using data from the literature, using data that we've got before. But in an ideal world, and this current situation isn't ideal, in an ideal world, to my mind, a good project is one that develops a wide range of skills. So ideally, if you were doing a project with me, you would practice a number of different aspects of chemistry and science. So you would make something, you'd do some synthesis, you would actually make a polymer. Once you've made a polymer, you have to characterize it. You need to know what you've made. So you'll use techniques, some of which you may be familiar with, perhaps NMR, for example, but also other techniques with, such as gel permeation chromatography, which is used to determine the molar mass distributions. You need to know about the material that you've made. You may well look at the effective surface area using sorption analysis. And then you would go on, ideally, to make a membrane, depending on the particular focus of the project, and to test it in some way. So, for example, you might be testing it for carbon dioxide capture. You'd be looking at carbon dioxide and nitrogen, or carbon dioxide and methane permeabilities, depending on the application in mind. How much of that we'll be able to do in the current circumstances is a big question mark, because of course you will not be able in the next year to spend as much time in the lab, and we have to have a sort of a backup plan, because we don't know exactly what will happen, that quite a lot of what you do would be out of the lab, but it will still involve many of the same basic elements. Does that answer the basic question?
Yes, yeah, definitely. That was a really good answer. So kind of more on the chemistry side of what you've been discussing, someone's asked, if you can call some molecules intrinsically microporous, does that mean that you can have ones that aren't intrinsically? So can you term polymers microporous that wouldn't be on their own?
Yes, absolutely. And that's actually why we said intrinsically microporous, because the normal route and the way in which most membranes are made is that you take a polymer which isn't particularly porous and you effectively put the porosity in by the way it's processed. So that can involve adding another component, which is then removed. Most membranes are actually made by a process, it's often called phase inversion. So effectively what you have is you have a polymer and a solvent, and you're making either a film or a fiber. It's usually a hollow fiber, but then you actually immerse it in usually water coagulation bath, which means that the outside precipitates very rapidly, but solvent is left on the inside, which ultimately is removed and creates holes. So there are many different ways of creating effective porosity. But the difference with our polymers is, if you like, we go right back to the chemical structure. We try to devise a chemical structure which, to a large extent, innately has that porosity. And then on top of that, we may do processing to tailor it or to adapt it. But yes, that's a very good question. And the reason we use the phrase intrinsic is to try to differentiate what we're doing from what you might call the normal approaches of getting this sort of properties into a polymer. I should say, as research goes on, you discover life is always more complicated than you thought. And our current research is showing that we actually get quite a variety of structures. It's not quite as simple, because there are defects and branches in the polymer, which are actually quite important for the properties. The stories, as often the case in research, is a little more complicated than we might have said and hoped initially, but the important thing is we get materials which have very interesting properties, and we're learning and understanding more about it all the time.
Fab, great. So next question. So moving on to like the graphene side of what you've been discussing today, In terms of application, is graphene better than molybdenum disulfide because they are used in similar applications, and this is without concerning the higher cost of the molybdenum disulfide?
So like so many things, it all depends on the application. There isn't a simple answer to that. When you're dealing with materials, then any material actually has competition. If we think about, if you want something that is highly conductive, then graphene has got extraordinary electrical conductivity. But it's actually in competition with indium tin oxide. But indium tin oxide you can't make into flexible things. Graphene potentially you can, which is its advantage. But now other materials are coming along which will potentially compete with graphene. So in any application, there is always competition. And of course, for every materials chemist trying to push one material, there's another materials chemist trying to do better with a different material. And which wins out at the end of the day depends on a whole range of things. And it's not usually the best performing material, because in terms of actual commercial application, it's other factors like the costs, the ease of producing it on a large scale, the supply of raw materials, the environmental factors involved with how it's made and used, which will actually determine what is likely to actually be commercially successful. So we think about polymers for membranes. There are actually only a very small number of polymers that are used on a large scale in membranes at the moment. There's thousands which have been studied in the labs, but only a small number are actually in commercial use. And they're not the best polymers for the job, but they're the polymers that are understood, that can be made on scale, that can be made economically, and the engineers are confident in using them. And with any new material, you have to build the confidence of the user as well as demonstrate the performance that you can achieve. So to go back to graphene and molybdenum disulfide, it all depends on the application. In some, one will win out. In some, another win out. In some, something else will win out.
Fab. No, that makes sense. That's fab. On kind of a different note, people are asking and are interested in how you actually got into material chemistry and what made you decide to kind of go down this career path with this kind of application.
So that's a very, go back to when I was a PhD student. So this is for most of you, the prehistory, because I got my PhD in 1981. So it actually goes back to when I was thinking as an undergraduate, what do I want to do? And I decided I wanted to do a PhD. I did go for some job interviews, but I decided I wanted to stay and do a PhD. And I was interested in a lot of chemistry, but polymers interested me at that time, partly because I wanted to do research which was both academically interesting at a very fundamental level, academically, but also was potentially useful. Often there's this sort of division between fundamental research and applied research, and I see a spectrum. And actually some of the most interesting fundamental research is in areas where you can also see some clear applications. And I wanted to bring those things together, even as a PhD student. That's really why I went into polymers, because I saw it as something where there were some very interesting fundamental questions, but also something that's very useful. And that has stayed with me as I went into industry, then came back into academia. That has still been an aspect of the way I see research, as trying to both understand things, answer very interesting scientific questions, but also do things that are going to be helpful in tackling some of the problems we face.
Great, that's really interesting. That's really good. Kind of on a related note, someone's got a background in pure organic chemistry and they're doing PhD research in materials chemistry. So they're wondering how their organic chemistry would be beneficial for their research in materials. Okay,
so it depends on the materials, but of course in the chemistry department, then we have the first floor is all organic materials. So that's polymers, but it's also other organic materials used, for example, in organic electronics. So organic chemistry is very, very important. It's important for making monomers and materials. We can't cope without the organic chemists. Interestingly, in terms of teaching, I'm officially a physical chemist, but my research group has to use organic chemistry to make the polymers and use some inorganic chemistry to understand what's going on as well. The thing is that in research, most of the most interesting things to my mind, there may be my colleagues who disagree with this, but to my mind, the most interesting research tends to happen at the boundaries between traditional disciplines. That applies, I tend to work at the boundaries between chemistry, physics, material science, and chemical engineering. Within chemistry, I work at the boundaries between organic, physical, inorganic chemistry, because it's where these different bits of a subject come together that you find the most interesting questions and also the most interesting opportunities. And so organic chemistry is absolutely essential for materials, but you've got to think, yes, I need the organic chemistry, but I also need to understand the properties, the physical aspects, the engineering aspects of how it's going to be applied. So if we're a good all-round scientist, we won't be too narrowly focused. We'll use our specific skills, but we will make use of them within a much broader context.
Great. Going back to kind of the chemistry of what you've been discussing, someone has asked, how do you decide the pore size of the polymer used for purification? Is it based on the pollutant size? And if so, will that require a polymer design for a specific contaminant? And would it be possible to design like a multifunctional one? And how would you go about that?
Brilliant question, and there's so many answers. So the first thing, if we're thinking about a membrane process, they're actually the simplest model. Scientists use a model to try to understand a process. The simplest model is actually what's called the solution diffusion model, because that brings out the fact that there are two different things to think about if you want to actually bring about a separation. And those two things are actually, first of all, actually, how the thing you want is going to get into the membrane. So that has to do with what we can call solubility or sorption. And the other thing is about how it moves through the membrane, and that is a process of diffusion. And both of those things are important, and in different case situations, one or the other may be more important, but they both contribute to how things permeate and ultimately how things separate. And depending on what you're trying to separate, one or the other may be more important. If we're thinking about, say, separating nitrogen from oxygen, in the first instance, it's primarily about the diffusion. Now, they have quite small differences in sizes. So you're looking for something where there's a very precise, effective size. It's not quite as simple as if it's too small, the molecule will get through, because there's actually a lot of movement in even a crystalline material. And these materials aren't crystalline, they're amorphous. They have no regular structure at all. But things will get through spaces that they should be too big to get through, but also things will have difficulty in getting through large spaces because of the energy barriers involved. So it's a little bit more complicated than just the size, but essentially the diffusion term ultimately relates primarily to the sizes of the spaces. But the other important thing is the sorption term. And that is a combination of the size of the spaces, because actually little spaces sorb more strongly, but it's also about interactions with the material that you're using. And so if we ask, why do our polymers really love carbon dioxide? It's a combination of spaces. It's also carbon dioxide, actually, it's a what we call a quadrupolar molecule. It actually interacts quite strongly with certain things in the polymer. So it will permeate through our polymers faster than hydrogen, which is a much smaller molecule. Most polymers, hydrogen is the fastest molecule for permeation. But in our polymers, carbon dioxide is the fastest molecule. And that's because the diffusive term is added to by a sorption term. So it's balancing, for a particular separation, these different absorption and what creates separation in terms of diffusion. And it's quite a complex thing, because if you push up the sorption too strong, we've done this, we can take our pollen, we can chemically modify it to sorb carbon dioxide even more effectively. And yet when we do it, we overdo it. It actually holds onto the carbon dioxide so strongly, it no longer diffuses through the polymer. So the selectivity actually drops down. So it's a very delicate balance, getting it right between the sizes of the spaces, which affects the diffusion, and the interactions with the actual chemical structure that you're dealing with that enhances or changes the sorption properties.
Great. So just one more question to kind of wrap everything up before we finish. Where do you see this research going next, and what's like the future career scope in perovskite research as well?
With research, anyone who says they know where it's going is a little naive, because the excitement of research is that tomorrow it can suddenly head off in a totally unexpected direction. When we started working with PIMS, we were actually thinking about heterogeneous catalysis and not about membrane separation. I was working with membranes, but a totally different area. But we actually opened up a whole new area of research, and that is often the case. But where I hope my own research will go actually is to try to push some of the ideas we've been talking about towards something that people will actually use. I want to see more examples of what we've developed actually out there helping people in the real live world. So that's what I'm very keen on. But all of in materials, the thing which makes materials chemistry in a sense, as much as anything else, is the fact that there's nothing that we do which we don't have an application in mind. That we're always pushing it towards something, even though we may end up finding that it's actually useful for something completely different. And that's true of all of the materials. There's lots and lots of exciting new materials that can be used. And it's wide open for you if you want to get involved in materials chemistry research, perovskites or anything else that might interest you.
Brilliant, fab. Well, thank you so much for taking the time to give this talk, and thank you as well for everyone for attending. We will shut this room now, but before we go, just a quick reminder that you can submit a piece of work summarising this talk if you want to get a certificate of participation. And yeah, just look out for more information and the recorded talks on the ChemSoc and past social media accounts too. So thank you, everyone.
Thank you, everybody.
Thank you so much. Thank you, Professor Budd. That was brilliant.